Yes, here. So, series. What we know so far about series. We have basically talked about, like in terms of real specific details, we've talked about two different important types of series. One is the geometric series. Those look like this. A times r to the power n minus 1, n equals 1 to infinity. And this thing converges to, a over 1 minus r when absolute value r is less than 1, and diverges when absolute value r is greater or equal to 1. So this is what we talked about for most of the time last time, the series a times r to the n minus 1. So if you're looking at a geometric series, then you can figure out what the a and the r are. The a is just the first term of the series, and the r is called the common ratio, which is determined by dividing typically you would divide the second term divided by the first term. All right, that was the geometric series. And then we also discussed, and this is just kind of a one-off, but this is the harmonic series. And that is this special one, just 1 over n equals 1 to infinity. And this diverges, and that's really all there is to say about it. 1 over n, the harmonic series, is what that's called, and it diverges. All right, those are the important two examples. Unfortunately, you just kind of have to remember which is which. The geometric is powers of the same number, and the harmonic is just 1 over n. So this one is, 1 plus a half plus a third plus a fourth plus a fifth. If you add that up infinitely many terms, it diverges. That is, that sum grows to infinity. All right. So what I want to talk about, first of all, is one kind of leftover thing that we could have talked about last time, but we ran out of time, and then some more general things about series. One thing to notice, in all cases, when it converges, when a series, something an, I'm not talking specifically about those two examples, I'm just talking about any series that actually converges. When this converges, it is necessary for the sequence an to equal 0 when I take its limit. When the series converges, it's necessary for the limit of the sequence to be 0. I'm going to try and, this is, I don't know, maybe confusing. If you think about this in the proper way, this becomes kind of an obvious statement, although there's a lot of technicalities here. But what I'm saying here is, here you imagine you have a sequence and you're adding up all of them, infinitely many things. You're adding together infinitely many things. And if that actually converges, that is to say, when you add up all of these infinitely many things, it adds up to only a finite number. It means those individual things that you're adding, they have to get really small in the limit, all right? Because if they didn't go to 0, then there's no way that adding them all together would give you a finite number. It would just go to infinity. But I want to talk about, this is actually a theorem, and I'm going to write it in slightly more technical language, I guess, although not really. It just is going to say, if the sum n equal 1 to infinity an converges, then lim n goes to infinity an equals 0. And I want to talk about why this is true, or try and, I think like I said, on some kind of intuitive level, I hope that this seems clear to everybody. Because if the limit here did not equal 0, that means the things you're adding together are not especially small. They maybe if this limit equals 2, it means you're trying to add together infinitely many things, each of which is about 2, which of course that's not going to add up to a finite amount. So anyway, if you want this to actually converge, this limit has to be 0. There's actually kind of a cute little proof of this. So I'm going to write this as a proof. It's a cute proof that has an important idea as part of it. So I'm going to call S this sum of the entire series, which converges. All right, so since it converges, that means S is a real number, right? It is the sum of all the terms in this series. And I hope everybody remembers what the series means. So the lim of n goes to infinity. Sn equals s. Remember, Sn are the partial sums. Technically speaking, that's what it means when you say this series converges. It means the sequence of partial sums converges to this number s. All right? But, check it out. If I do Sn minus 1, what is that? Sn, remember, is a partial sum. That is, Sn is the sum of all the a's, a1 plus a2 plus a3 up to an. And this one is the sum of all the a's, but only up to n minus 1. And what can anybody say, what do you get if you subtract these two? This is adding everything up to an. This is adding everything up to an minus 1. Maybe I'll write that out. It'll become clearer. This goes, sorry, not 1. a1 plus a2 plus an minus the same thing, but only going up to n minus 1. a1 plus a2 plus a n minus 1. What remains when you subtract? Yeah? Just an, right? All the other ones cancel because they are repeated. Like a1 here, a1 cancels a1, a2 cancels a2, and so on. Everything will cancel except for an is like the only thing that's going to be left over here, because everything else appears in both parentheses, and so it will get canceled. So this is an. All right, so I'll just write that again. Sn minus 1 equals an. And now I'm going to take the limit through the whole thing on both sides. So now take lim n goes to infinity of everything. It'll say lim n goes to infinity Sn minus lim n goes to infinity Sn minus 1. This is because you can split a lim across of a plus or a minus sign. That's one of the rules about limits. Equals lim n goes to infinity an. Based on what we've already said here, lim, I'm going to try and simplify what I see on the left side. Lim n goes to infinity Sn is s, right? So that's s minus. What is lim n goes to infinity Sn minus 1? I said there was sort of one important idea as part of this proof, and this is it. Lim n goes to infinity of Sn minus 1. Any thoughts? This is a little abstract at this point. This says when you look at those sequence of s's and go down the end of the sequence forever, it converges to s. What about this? This means you look at that same sequence of s's, you go down the sequence forever, but you look at like the second to last one instead of the very last one. What'll this converge to? I would say this also converges to s. All right? What this means, this equals s means way down the list, as you continue forever, the values get closer and closer to s. This means way down the list, the second to last value gets closer and closer to s. But that's automatically true, right? If all these values get close to s, then it's also true that the second to last value also gets close to s. So here, s also. The s's on the left cancel, and it says 0 equals lim n goes to infinity an, which is what we wanted to show. All right? That was the goal of the proof, was to show, can you remember at the very beginning? Then lim of an equals 0, right? And that's what it says right here. The important fact, though, that I wanted to bring up is this somewhat weird step right here. You see that line there? I would describe that in this way. Well, this is what I'm saying. If Sn converges to S, then so does Sn minus 1. All right? This is a sort of strange, I don't know if this is strange. It looks weird when you write it down, but it definitely is true. Sn converges to S means eventually the terms in this sequence get close to S. Sn minus 1, those are the same terms. They're just sort of behind by 1. But when you're going out to infinity anyways, it doesn't matter. They still converge to S. That was the important fact that was used right here. All right, anyway, otherwise it's just some sort of cute tricks here. The fact being demonstrated was if the series converges, then the individual terms go to 0. All right, you can actually use this to show that some series diverge. So this theorem can show that some series diverge. For example, now this is an example that we've already talked about, but this series minus 1 to the n equals 1 to infinity. This one, even without, we talked about this before by looking at the partial sums individually and then taking the limit of the partial sums. But even without thinking about that, you can just say those individual things inside the sum, they don't go to 0, do they? They're just plus 1 or minus 1 each time. And so because of that, it means the whole thing cannot converge. Because the theorem says if it converges, the terms must go to 0 individually. And they don't in this case. So here, these guys, these ANs, don't go to 0. So the series doesn't converge. And that's really all you have to say. All right? Those individual terms don't go to 0. And so the series doesn't converge. All right, or here's another example. How about the sum of sine of n? This is a very weird series. Sine of n. What you're looking at here is sine of 1 plus sine of 2 plus, etc. Infinitely many terms. Anybody remember what is sine of 1? The answer is, I don't know. Sine of 1 radian is not anything. I mean, you can do it in your calculator. It's something, but it's not anything, if you know what I mean. It's not any kind of nice number. It's just some random number that you get if you plug sine of 1 into your calculator. It's like plugging your phone number into the tangent function. It doesn't equal anything special. It's just something. Sine of 2 is also like that. What you have here is basically a whole bunch of numbers. I really have no way of knowing what these answers are. Some of them are positive, some of them are negative, because the sign is sometimes positive, sometimes negative. In theory, the sign can sometimes equal 0, but it's not going to here because the sign only equals 0 at multiples of pi, and none of these are multiples of pi. But anyway, can you say if this converges or not? I would say on its surface, it's not easy to say if this is going to converge or not, because like I said, some of these things are positive and some are negative. So it may be by some magic they all end up canceling each other out. But you can by this same argument here. So the sequence inside here, sine of n, an equals sine of n. This does not converge to 0. Because if you just keep on plugging bigger and bigger numbers into the sine function, it doesn't go to 0. They just you get whatever, the graph of sine goes up and down forever. It doesn't eventually go to 0 when you plug really big values. So an equals sine of n doesn't converge to 0, which means, so the series diverges. This is something that's actually kind of hard to show otherwise if you don't know about this little trick. Because it seems at least possible in theory that these numbers, because some of them are positive and some are negative, they might end up canceling out and converging to something, but in fact they do not. All right, that series diverges. Okay, another. How about, this is the last one of this type. How about the sum of 3n cubed minus 7n over n cubed? Does it converge or diverge? This one diverges, again, for the same reasons. So I'm going to look at So if this were in the homework or something like that, it might say something like, show that this diverges. And because we've just been talking about this theorem, it might occur to you, I'm going to show that it diverges by demonstrating the individual sequence terms do not converge to 0, all right? So I would like to consider the lim of 3, sorry, my handwriting here. This is supposed to say n cubed up top. 3n cubed minus 7n over n cubed. Take the lim of the individual terms, as they say. Can anybody say, what is that limit going to be? Using some, you can think of that as a continuous function, as if they were x's everywhere. What would the limit be there? And remember some cute tricks for limits of fractions of polynomials? I would rewrite this as a real valued limit of a continuous function. X cubed. Anybody remember tricks such as this? It's 3. Yeah, why do you say it's 3? I agree.
It's the same degree.
Yeah, this is that thing where you remember, okay, if the degree on top is bigger, the limit does not exist. If the degree on bottom is bigger, then it's 0. And if the two degrees are equal, you take the ratio of the leading coefficients. That's the situation here. If you totally forgot about all that, you could actually use L'Hopital's rule on this, because if you just try to evaluate, you'll get infinity over infinity. But anyway, this is 3 over 1 is how, if you remember those tricks, which I hope you do, now that I reminded you. All right? But anyway, this is enough to show that the original series diverges, because the terms, their limit is not 0, it's 3, right? So the terms don't approach 0, and so the series diverges. Right. This is a nice way to show that a series diverges, if you can show that the individual terms do not have limit 0. In this case, they have limit 3, and so it can't diverge. It can't converge, it must diverge. It means when you try to do the series, you're basically adding up infinitely many things, each of which is around 3, and so it's going to be infinite when you try to do that. All right, infinitely many 3s. It's just infinite. All right, great. This is something we don't need to spend a whole lot of time on, but we have rules for limits about how you can add together limits, and we talked about those rules are still true of sequences. When you add two sequences together, the limits of each sequence will add together. There are similar rules for serieses, so I'm just going to write them down once. We don't really need to talk a whole lot about these because these are things, they are going to look the same as usual when we talk about limits of sequences or anything else. So it says if the sum of an, n equals 1 to infinity, and the sum of bn, n equals 1 to infinity, both converge, then you can do a bunch of tricks with adding them together or subtracting them or whatever. And there are many of these, but I'm just going to write down sort of in my opinion, the most important ones. And I think everybody can guess what I'm going to say here. The series an plus bn is, what do you think? This is like rules for limits. Maybe I shouldn't have said everybody knows what I'm going to say here. Nobody wants to say it. Any ideas? Yeah?
You can make it 2 sums.
Yeah, you can make this 2 sums. The series of an plus the series of bn. Exactly right. This is basically the same as our limit rules because remember each of these series represents a limit of partial sums. And so if that series is a limit of partial sums, you can split it apart into these 2. All right. This rule, it's necessary that these converge in order to do this. But if those 2 things on the right-hand side actually exist, then they equal the thing on the left-hand side. There's one with a minus, and it's exactly what you think it ought to be. The sum an minus the sum bn. Products and quotients are a little more complicated. So at this point, at least, we're not going to talk about products or quotients. Maybe I'll write a line sort of in red, meaning this is actually not a rule. But if I have something like this, Bn, is it like if you're not thinking about anything, this is what you would naturally want to say. This is definitely false, though. This is absolutely not true, because what you have over here, this is like A1 plus A2 plus A3 plus blah, 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 multiplied by B1 plus B2 plus blah, blah, blah. Does that actually, is that the same as, A1 B1 plus A2 B2 plus A3 B3? The answer is absolutely not. Like, if you actually wanted to multiply this out, you'd have to do a ridiculous, like, infinite FOIL thing, and you would get many, many terms, not just A1, B1, A2, B2. You would also get things involving A1 and B2 and so on. So this rule, maybe you wanted that to be true, is definitely not true. There is another version of this, which is kind of true, but it's far more complicated than that. And also for quotients. If you just try to write what seems like the natural rule, it's not true. One last thing, though, that is true, it's just about multiplying a constant. So if I have a constant multiple on the inside, you can factor the constant out. You can. It says can right there. You can factor the constant out of the sum, all right? Isn't that hilarious? All right, so these are just simple things. Every so often we will want to do these rules. We're not going to really talk about them very much. You can basically just do them without even thinking about it. You can split up a summation sign like this, and you can factor a single constant out of the sum like that. You cannot combine products or quotients in similar ways, though. All right. Great. Let's try one example where you use these rules. So we can use these sometimes to compute series. For example, how about the sum 5 over 3 to the n minus 3 to the n over 2 to the 2n? All right. Now, this by itself is too complicated to do like we did last time. All of those series were just one thing inside of the series with some powers of n in it. But here, there are two terms in each term of the series, right? And they don't use the same, our techniques from last time are thinking of this as something like r to the n. But these don't use the same r's between the two terms there. So it's not a big deal. The simple solution to this would be to split it apart into two series and then handle each of those two individually. So I'm going to split as 5 over 3 to the n minus the sum 3 to the n over 2 to the 2n. And each of those I am going to do separately using our techniques from last time. And those techniques involve figuring out the a and the r. Each of them are geometric series. So these two here, these are both geometric series. And I'm going to do them separately. And then add together the answers, or subtract if you prefer. Separately. All right, they're both geometric series, so we do them separately. So maybe I'll just do the first one here. 5 over 3 to the n. I hope you remember the method for this is to find a and r, and then the answer becomes a over 1 minus r, right? That's how we were doing these last time. So the a, towards that end, I'm going to just write down the first two terms, and that should be enough. So a1 is 5 over 3, and then a2 is 5 over 3 squared, right? And then what about the a and the r? Anybody remember what's the a here? This is what we're doing at the end last time. Yeah?
5/3.
Yeah, the A is just the first term, which is always easy. You don't have to calculate anything. A is 5/3, and then the R is called the common ratio. It's the second one divided by the first one. So here it would be 5/3 squared divided by 5/3, right? The 5s will cancel. You have to simplify this fraction. If you prefer to write in terms of reciprocals, this would be 5/3 squared times the reciprocal 3/5, right? That's a third. I think I got that right. It's easy to mess up the fractions there, all right? So anyway, that means that you check that this converges. R being a third, that is less than 1, and so it does converge. And so this first one converges to, it's A over 1 minus R. That would be 5/3 over 1 minus 1/3. So that's 5/3 over 2/3. Cancel them 3s, it's 5/2, all right? This is not my final answer. Remember, that was only the first part. I had split this big series into 2 parts. The first one converges to 5/2. And then we can also do the second one. Let's do the second one. The second one says sum 3 to the n over 2 to the 2n. And we do it in exactly the same way. So I'm going to write the first term. A1 is 3/2 squared. That's, well, I'll just leave it like that. And then A2 is the second term, 3 squared over 2 to the 4. I'm plugging in n equals 1 and then also n equals 2. And then I do the A is the first term, so that's 3/2 squared. And R, there's no B, R is A2 divided by A1, also known as, you could also write A2 times the reciprocal of A1, so that would be 3 squared over 2 to the 4 times. The reciprocal of A1 would be 2 squared over 3. Cancel stuff out, I get 3 up top and 3/4, I think, right? 3 remains in the numerator and then 2 squared in the denominator, which is a 4. All right, I think I did that right. And so what's my final answer? Sorry, I'm not ready for my final answer. That was just the R, right? So that means this one converges to A over 1 minus R, which in this case is, A is also 3/4, right? So it's 3/4 over 1 minus 3/4. That's 3/4 over 1/4, which is 3. All right? So that means my second series there converges to 3. I hope I didn't. It's, of course, easy to mess up the numbers here, but I think I'm doing all right. All right, so anyway, now I can say my final answer. Do we still remember what we started with this, right? So finally, so this is, the first one was 5/2 minus 3. That's my answer. -1/2, I think. Right? That's how we do it. I got one for you all to try. I hope that made sense. It'll take you a few minutes to work out all the details, but nothing too fancy. How about evaluate the series? The sum 3/2 to the n plus 4 to the -n over 3 to the n over 2. How you like that? See what you think. 1 divided by the first factor. Good here. Yeah. Not very.
I don't know, like, for some reason, does it click in my head? Do I just multiply the 2 on top?
Not quite. I find it easier to think of in terms of, so this divided by that is the same as this.
So you would just use 6 over 12.
Yes, yeah, 3/4 times 2/3. Yeah, right. Okay. Yeah, this is that. The R is always the second one divided by the first one. Yeah. So you have 3/4 divided by I'm going to start writing my answer. Everybody seems to be doing well here. As long as you get the fractions in the right places. Can we talk about these? I don't know if everybody is finished or not, but they're pretty routine as long as you don't mess it up. I hope I didn't mess up the first. So I did the first one first. I got R was a half. Make sure you divide in the proper order. It's the second one divided by the first one. And I got A, the first one is 3/2. So I ended up with 3 as what the first one converges to. Anybody agree? Yes, okay, great. And then the second one, 4 to the minus n. This one's a little more complicated looking. 4 to the minus n over 3 to the n over 2. So A1 is 4 to the minus 1 over 3 to the 1/2. A2 is 4 to the minus 2 over 3 to the 1, I guess, right? 3, just 3 down there. And so my A this time will be 4 to the minus 1 over 3 to the 1/2. You can write that as 1 over 4 root 3, or there's many ways to write that, but I suppose you could have just kept it like I wrote it. And then anyway, the R would be A2, which is the second one, 4 to the minus 1/2 over 3 divided by the first one, 4 to the minus 1 over 3 to the 1/2. This, if I write it as multiplying the reciprocal, which I find easier, would be 3 to the 1/2 over 4 to the minus 1, like that. And then cancel the 4s. This is a little complicated. I think I end up with a 4 on the bottom, and then a 3, and also a root 3 on the bottom. I think it's that. Anybody agree? If you simplify these fractions, it's a little weird, but I figure that's what you end up with. Yeah? Okay, and so that means for this one, it converges to A over 1 minus R. By the way, you should be checking for yourself, at least in these cases, the R is always less than 1. Because if the R ends up being in absolute value, R is 1 or greater, then the thing diverges. But this is less than 1. Anyway, it's 1 over 4 root 3 divided by 1 minus 1 over 4 root 3. And I don't think it's worth trying to simplify that. You could, I suppose, multiply through by 4 root 3 on the top and the bottom. That would turn this into 1 over 4 root 3 minus 1. That's a little nicer, but I don't care so much about that. So anyway, my final answer would be final ands. the sum of those two answers. I had the 3 and then this thing. So it's 3 plus 1 over 4 root 3 minus 1. There you go. I hope that's what you got, something like that, yeah?
I got root 3 over 12 for r.
3 over 12.
Root 3 over 12.
Anyone else? I think that's the same as 1 over 4 root 3. Because root 3 in the denominator, this is the same as 1/4 times root 3 over 3 to all those high school teachers who said, don't put root 3 in the denominator. So that's the same.
Okay.
Yeah, if you simplify slightly differently, you'll get root 3 over 12, which is also correct. All right. For once, a complaint, and I'm not wrong. I appreciate it. Nobody's wrong, right? It's the best kind of complaint. You're both right. Okay, great. Let's talk about something a little different. So this is actually a little kind of theme that we're going to be talking about for the next few of our topics as far as sequence and series goes. What we've done so far, that was kind of the end of our basic introduction to series. Yeah, the clock is messed up in here. The clock in this building, when we do like the daylight savings, it takes them like several weeks for them to change the clock. I think nobody really knows. I certainly don't know who is in charge of those clocks. It's the entire building has these clocks and they're all in sync, but I don't know where the button is to fix them all at once. I have tenure, but I don't have that much power to change the clocks. Okay, what we're going to be talking about, this is kind of a long-term theme, is what we call, convergence tests. That is, if I show you a series, can you tell me if it converges or not? This turns out to be actually a very hard question in general to answer. And there is no kind of magical theorem that will tell you the answer in all cases. If I just show you a series, so I'll write it this way. Given a series, I would say in generally, it's hard to tell if it converges or not. And this is actually true, like, I don't mean just hard in the context of our class here, but I mean in using the full power of all of modern mathematics. There is no single known method which can tell you this all the time. If I show you a series, can you tell me if it converges or not? There are many, many individual examples and many, many sort of individual tricks that you can try, but there actually isn't a general purpose method which always works. What we have are sort of a bunch of what we call convergence tests. So these convergence tests are individual, tricks that you can try which might tell you if it converges or not. And there are several different tests that we're going to talk about. The first one we're going to talk about is the integral test, which has to do with translating your series into an integral. There are other ones. There's something called the ratio test, the comparison test. There's a bunch of different tests. So if you are, talking to someone in the club about this and they're like, I just don't know if this converges or not, you can say, hey, well, did you try the ratio test? She'll say, I have a boyfriend, right? That's convergence tests, though. That's what we're going to be talking about for the next, few times. Convergence tests, tricks you can try which might tell you if it converges. And there is no general purpose trick to answer this question, but there are individual different things that you can try. And most examples that you will ever encounter in your life, somebody somewhere knows how to do it. But actually, this is not true in general. There are some examples of series where none of the tricks works, and nobody really knows how to figure it out. All right. Sometimes here's an example. Actually, a cute example. of a series which is very hard to tell if it converges to, remember that the sum 1 over n diverges. What about the sum 1 over n squared? All right. These terms individually, so 1 over n is, of course, 1 plus a half plus a third plus a fourth, etc. And the fact that this diverges, it means these fractions, they are getting kind of small, but apparently not small enough, because it's still true, even though these fractions are getting small, it's still true that if you add them all up, you will basically get infinity, or they do not actually add up to a finite amount. All right? What about 1 over n squared? Of course, this would look like 1 plus 1/4, 1/9, 1/16. Here I'm just adding up the squares. These guys are even smaller than those ones. And it turns out, although this is not obvious at all, this one actually does converge. This one actually, it does converge to, anyone want to guess what it converges to? It converges means if you try to add these up together, sort of all infinitely many of them, it actually does add up to a specific number. Anyone want to guess?
2.
2 is a great guess. This was a bit of a trick question. Nobody ever would have guessed the correct answer. This is a true fact. The sum n equals 1 to infinity, 1 over n squared is, I'm sure this would have been your second guess, pi squared over 6. How do you like that? This was first proved by a famous mathematician named Euler in the 1730s, all right? But I am just mentioning this to suggest that adding up a series like this sometimes involves crazy methods and insane tricks. Because just think about adding these up. Whatever you're doing, it would have to be pretty insane if that could be the final answer, pi squared over 6, when these numbers have nothing to do with pi, in my opinion, all right? But it turns out actually these numbers do add up to pi squared over 6, using some very fancy tricks here. So around this time, the 1800s, there was huge amount of interest in learning new techniques for adding up series. And this is something that people are still working on to this very day. So all of that just to say, the question of saying whether or not a series converges, and furthermore, what does it converge to, that question is super hard in general. And you will often get crazy answers like this, even if you start with an ordinary looking sequence like that. All right. What about 1 over n cubed? Actually, I'm going to talk a little bit about that probably next time. But you could also, of course, think about 1 over n cubed, 1 over m to the 4, etc. It turns out 1 over n cubed is just some number that is an irrational number that actually has no expression in terms of pi or e or anything. It's just another weird number. Strange but true. Let's talk about the first of our tests anyways. This is called the integral test. And the integral test is a way of showing that a series converges by viewing it, instead of a series, you view it as an integral, and then hopefully you can use tricks to evaluate the integral. That's the idea. So the idea here is to show that some series converges. I will say, hopefully, this is the plan at least, change it into an integral, or I will say convert it to an improper integral. This series is, of course, a sum up to infinity, right? But we should be able to sometimes you can convert this into an integral up to infinity and then use our integration tricks to work with that, right? Because we don't really have a lot of series tricks, but we do have a fair number of integration tricks. So the strategy is hopefully convert it to an improper integral and then use integration tricks. All right, that's the basic concept of the integral test. Let's try a specific example here. How about, actually, let's, you can use, you can do this to show that the harmonic series, 1 over n, diverges. So we actually did talk about this last time by using some weird tricks to rewrite the terms of the sequence. I don't know if you remember that. It's not important if you remembered the tricks, but you can actually use an integral comparison to show that this sum diverges. Check it out. I am going to represent that sum, 1 over n, as if the terms come from doing rectangles. And I'm going to draw this. So I'm going to draw it this way. This rectangle has size 1, then I have a rectangle of size 1/2, then a rectangle of size 1/3, 1/4, and I'm trying to add together those areas, right, forever as you go off to the right. And you will realize, this is not an obvious idea, but this is what we're trying to talk about. Comparing that to an integral, this can be compared to the integral of this function. This is the function 1 over x. Maybe I'll use a different color here, just so you can see it better. I'm comparing the series to the integral. This is the function 1 over x. Actually, that series is equal to one of the rectangular approximations of the integral if you were trying to write the integral as a Riemann sum, which I'm not really trying to do that, but you could think of this whole scenario in this way. So this series, n equals 1 to infinity, 1 over n, this is actually, if I wanted to compare the areas, that series from here, looking to the right, the series is greater than the area under the curve, right? Because the series involves those rectangles, but they're sticking out. They are bigger than the area under the curve. So the series, 1 over n, is actually greater than the improper integral 1 to infinity, 1 over x dx. Right? The series is greater than the area under the curve because you can see the rectangles are sticking out. So the yes, greater than, yeah. The series is greater than this business. All right, and we can find that integral, right? That integral is something that we know how to do with our improper integral tricks. So do this integral right here. This I would start by changing it into a limit of the integral 1 to t. I hope everybody, this is an easy example of an improper integral. I'm going to do the antiderivative. You try and do the integral as much as you can, and then take the limit at the very end. What's the antiderivative 1 over x?
ln x minus 1
Yes, it is natural log of x, natural log absolute value x. And then I'm going to plug in 1 and t. Great. Plug them in, I get lim t goes to infinity. ln t, absolute value t, I guess it doesn't matter because t is going to go to infinity, minus ln of 1. ln of 1 is 0. And what is ln of t as t goes to infinity? That limit is infinity. So this diverges. This part right here goes to infinity. That's because the graph of ln looks like that. And it just continues to go up. It goes up kind of slowly, but the graph of ln of t, as t goes to infinity, the graph also goes to infinity. All right? So can we summarize everything that we said here? We said the series 1 over n is greater than, as the lady in the phone said, the series 1 over n is greater than the integral 1 to infinity, 1 over x dx. and the integral, this integral actually goes to infinity. That means the series itself also must go to infinity. If the series is bigger than the integral and the integral is actually infinite, then the series also must be infinite. So the original series, 1 over n, also diverges. That's the idea. This is the general procedure when you're trying to do the integral test. All right. So I'm going to try and write this down formally, and then we'll try some other examples here. Can I just say one thing here? This trick to compare the rectangles to the area under the curve, this trick actually is only going to work if the function is a decreasing function. That's because when it's a decreasing function, all these rectangles will be sticking out, they're hanging over, and so we are guaranteed that the series area is greater than the area under the curve. If the function was sort of going up and down, then some of the rectangles would be outside and some would be inside, and then you wouldn't be able to say for sure one is bigger than the other. But it is possible when the function is decreasing, these rectangles will always be greater than the area under the curve. All right. So what I'm going to say here is, I'm going to write this as a theorem, but if you like, this theorem is called the integral test. And like I said, this only applies when your function is decreasing. So this is a huge limitation just right away. You can only try this when your function is decreasing. But it says if f is a function decreasing on the interval 1 to infinity, this is where we're always trying to convert the series, which goes n equals 1 to infinity, to an integral, which goes x equals 1 to infinity. So in order for this to work, the function f must be decreasing on this real interval. Anyway, if it is, then you can do the integral comparison test. And what it says is, when the integral 1 to infinity, f of x dx, diverges, then the sum f of n equals 1 to infinity, also diverges. That is exactly the way that we explained it in the example that we just did. And the same is also true for convergence. So it's also true when this integral f of x dx converges, then the integral, the series n equals 1 to infinity f of n also converges. All right. Now the example we just did was of the first type, where the integral diverged and the series was bigger than the integral, which means that the series also diverged. For the second part, maybe I'll just try and explain in words why you should also believe this part. When the integral converges, then the series also converges. This would be if the integral actually adds up to a particular area. Do you know that the series also adds up to another area? The way to reason that out is, I'm going to kind of ruin my picture here, but rather than drawing the boxes where I put them, you could draw the same boxes, but sort of one position to the left. Just move every box 1 unit to the left. Then all of the boxes are under the area under the curve. And so in that case, you can say if the area under the curve is finite, then the area under the boxes is also finite, which is what this says. If the area under the curve converges, then the series area, which is all the boxes, also converges. All right? This is called the integral test, and you should remember what it says, especially this bit. It only is used for a decreasing function. If your function is going up and down or something like that, this is not a valid result. All right? let's try an example. Actually, we can do Euler's sort of ridiculous example. So let's try, here's a typical, this would be like a easy homework question about this. Use the integral test to show that sum 1 over n squared converges. N equals 1 to infinity. All right? The idea is we just convert this into one of these integrals, just like you can see on the top there. And if the integral diverges, that means the series diverges. If the integral converges, that means the series converges. So you change it into an integral, and then that will tell you whether or not the original series converges. So notice the way you build the integral. If you have the series, which has a function on the inside, you make the integral have exactly the same function. It's just in terms of x rather than n. So this 1 over n squared becomes the integral 1 to infinity 1 over x squared dx, right? It just turns into the same function, but now inside an integral instead of inside of a series. Now we should make sure that this is a decreasing function. So is 1 over x squared decreasing on the interval 1 to infinity? If not, then we just can't do this at all. But it is, right? If you were to look at a graph of 1 over x squared, it looks like this, right? This is a graph of 1 over x squared. And I only care about this part of it from 1 to infinity, right? But over there on the right-hand side, it really is decreasing. That means it goes down as you go to the right. All right? So is 1 over x squared decreasing on there? Yes, it is. So we can use the integral test. Because that function really is decreasing from 1 to infinity. All right? And so let's try and do it then. So we have to actually evaluate the integral, 1 over x squared dx. Again, this is a fairly straightforward. If you remember how to do improper integrals, I hope you do. This, I will turn it into a limit. Limit t goes to infinity, integral 1 to t. I'm going to write it as x to the minus 2. And then do the integral. Somebody say, what's the antiderivative? Yeah.
Is it negative 1 over x?
Yes, I was going to say negative x to the minus 1, but yeah, it's negative 1 over x. Okay, and then I got to plug in 1 and t. T goes to infinity minus t to the negative 1. Maybe I'll write it as 1 over at this point. Minus 1 over t minus negative 1 over 1. And this part here, when I do the limit, finally, this part becomes 0. And so my whole answer is just that other thing, negative 1 over 1, which is 1. All right? So the integral 1 to infinity 1 over x squared dx converges. Thus, the series 1 over n squared also converges. The end. It's important to point out, we still don't know what it converges to. So the answer of the integral is not the same as the answer of the series. Because remember, the integral, when we drew the pictures of the integral and the boxes, the area under the curve is not the same as the area under the boxes. It's just that one of them, if one of them is infinite, then the other one is also automatically infinite. And if one of them is finite, the other one is automatically finite. But they're not the same area. So we cannot conclude anything. I will just say parenthetically, we still don't know what this equals, right? And the integral test doesn't tell you that. It's just a test for convergence. It is not a method for evaluating the series. So we are able to verify that it converges, but we are not able to say what it converges to. In reality, it converges to pi squared over 6, but this is a crazy answer that you have no way of really calculating with these methods. All right. Can you all try? I got another. How about let's try to show using the integral test that the sum, this is very similar, 1 over n cubed converges. Using the integral test. When I put these questions on the tests, I'm not necessarily going to tell you which of the tests to use, although because the questions are numbered according to the checklist, you will usually know that I'm talking about the integral test or whatever other test. I'm going to write down what I got. This is basically the same as the previous example. Can we talk about this? It's really just the same as what we did before. I didn't notice anybody draw the graph of 1 over x cubed, although I hope you were thinking about it in the back of your mind. This method, remember, only applies if the function is decreasing from 1 to infinity, which it is right here. And so it is legal to do the integral test in this example. I'm not ever going to try to screw you by asking you to do it when you're not allowed to do it, but I might ask sort of, are you allowed to do it or not for this example, or something like that. Anyway, do the antiderivative. It becomes 1 over minus 2x to the minus 2, right? Evaluating at 1 and t, et cetera, et cetera. I got a half when I did this. I hope that, that you got a half when you evaluated the integral. Anyway, this converges. So the sum 1 over n squared cubed is what we're talking about, not squared. Great. Yeah. Any thoughts about that? In our remaining 5 minutes, I thought I might tell you a little something about, you can do this same procedure basically for any 1 over n to some power. So this same thing, this actually works for any sum 1 over n to the power p, where p is greater than 1. If p equals 1, that's the harmonic series, 1 over n, which diverges. But if p is greater than 1, what you get is, like 1 over n squared or 1 over n cubed or any of the higher powers. These things always converges when p is greater than 1. All right? This is referred to, these things, this is called the p series. And the values that it converges to are totally weird, though. Like, for example, when p equals 2, like, it's easy to show using the integral test that it always converges. But what does it converge to? Well, when p equals 2, it converges to pi squared over 6, right? This is that weird one that I said before. And I also said when p equals 3, 1 over n cubed, this converges to just some random irrational number that actually nobody really knows what it is. It's not known if it's related to pi or any other number. So this just converges to some weird number. Actually, when you use p equals 4, I didn't write it down. There is actually, so there's a nice formula in terms of pi for this one. There isn't for the next one, but for p equals 4 there is. It's a weird, strange but true thing. And actually there is a name for all of these things. So this thing, you can make a function, make this is a little far out, but make this a continuous function of p, right? You can imagine just plugging different numbers in for p and you get different answers. When you plug in p equals 2, you get this answer. When you plug in p equals 3, you get some other weird answer. When you plug in p equals 1, the answer is kind of infinity. So this function has some values which diverge. But this is called, there's a name for this, and this was actually studied by another famous mathematician that everybody knows. This was studied by Riemann, also known, for the Riemann sums. This function is called Riemann's zeta function. He used the Greek letter zeta for this, which looks something like that. It's a pretty nice looking zeta there, if I must say so. It's this. So you plug values of p in, and you try to measure what the value of the series on the right-hand side is. And I will just leave you, we got 1 minute on the clock. A big question that Riemann asked, so Riemann proved one theorem about the Riemann zeta function, which is the Riemann zeta function written in this way is not very interesting, but actually you can rewrite this as a formula in terms of the sequence of prime numbers. And this became very interesting to a lot of people. It means that in some sense, the randomness which we observe in the theory of prime numbers, if you want to study the prime numbers and how they vary, you can instead study this function. There is a deep connection between the two of them. And there's a big question, for which complex, this is kind of far out, for which complex numbers p will zeta of p equal 0? If you plug an imaginary number in for p, it's actually possible for some of these to end up being negative, so that this sum sort of magically adds up to 0. That's not possible if p is a real number, but if p is an imaginary number, that actually can happen. For which complex numbers p does the zeta function evaluated at p equals 0? This question is referred to as the Riemann hypothesis. Riemann had a specific hypothesis about which p satisfy this. but he was not able to prove it. And this is like in the late 1800s, Riemann was doing this work. And at the beginning of the 20th century, this became regarded as the most important unsolved problem in mathematics. And today, it remains unsolved. So if you want to, take a couple hours tonight, think about it. There is a $1 million prize associated with solving this problem, the Riemann hypothesis. If you figure it out tonight, let me know. I'll split the money with you. This is like the holy grail of, this is uncontroversial to say, the most famous and important unsolved problem in mathematics today. So check it out. All right, that'll do for now.